chapter 7 then. Stop.
We'll look at number 63. 63 looks at different things. Which is true regardless of how the reaction is carried out. The first one we're going to look at is QV.
What is this question asking for? Which is true for the amount of heat, regardless of how the reaction is carried out? QV. Does this make sense? This is close to the book's wording on this. And so this one, what are they asking for? Number 63. Is QV true for the heat, regardless of how the reaction is carried out? What do you think? Do you have any ideas? No matter how you do the reaction, you're going to get QV is QV. How about QP? How about delta U minus W? How about delta U of delta H? So think about those. We'll be right back. We'll get the exact wording. Let me read the question for you. Which expression holds true for the heat of chemical reaction, regardless of how the reaction is carried out? So, regardless of how the reaction is carried out, is QB true? You sure you say no? Why is that?
I think it's the same under endothermic, scenario 1.
Endothermic scenario versus exothermic scenario. Okay. Other ideas? Comments?
See, and I think, what are they talking about? Regardless of how the reaction is carried out, which is true? QV? Or, yeah, I think a lot of people aren't going to get. 63, well, listen, only one of the following expressions holds true for the heat of chemical reaction, regardless of how the reaction is carried out. Which is the correct expression and why? So I changed it a little bit. I just said, we're going to look at these one by one and tell me which is true regardless of how the reaction is carried out.
Automatically, you'd say D, D's. Right, but you know what? It depends on how you think about these things. Because what is QV? QV is the heat under, and how do we get heat under constant volume? We do it in a bomb. If you do it in a bomb, is there any work done? No, so delta U is equal to QV plus W, no work can be done, so delta U and QV are the same. And so if you say D, then shouldn't you say A as well? Well, let's take a look at these one by one. So regardless, this is very tricky, this question, and, the thing, I took, how many multiple choice exams I took when I was a student at UCLA? Did I talk about this? No? When I was a student at UCLA, I took a total of one class out of all the classes I took at UCLA had multiple choice. None of the other classes had any multiple choice tests. And there was something, I took the class which was paleobiology. And paleobiology has a reputation as being the easiest life science course at UCLA. And it was a pretty easy course actually, so if you're thinking about an easy life science course, that might be one you'd consider. It's easy because the multiple choice questions were straightforward, right? And so then I took a bunch more because I had to take the GRE exams, which are required for graduate school. So one of the GRE exams was algebra. And it's all multiple choice. And I already had 2 years of calculus, so I thought algebra is going to be so easy. I'm not going to study for it. And I didn't study at all. I didn't spend 1 minute even thinking about the GRE for math because algebra is just too easy for me. And then I took the test, and I got back my results. And my results were awful because when they look at the results, you're comparing yourself to all majors. All people who want to go to grad school take the same math test, whether you're in English or philosophy or whatever. And so normally the science people are supposed to get in the 90s and high 90s for algebra, right? But I didn't. I didn't even break into the 90s. And so that was a shock. One, it shocked me, and two, it shocked all the grad schools I was applying for. They said, why did you do so bad on the math during the interviews, right? Fortunately, they didn't care so much. They did bad. But I said, at the time I didn't know. I mean, how could I do so bad on the algebra multiple choice test? And so then I broke down and I bought, you could buy old exams for the math test. And then I read the questions carefully. And a lot of them were very tricky. They were worded in a way that you could automatically select the wrong answer if you weren't careful enough, right? And that always stuck with me because, I hadn't had that much practice yet. You have to take the GRE for this and the GRE for that, and they're all multiple choice. And so then I thought, wow, even though algebra should be so easy for me, it was the way the questions were worded that threw me off. And then I thought about, how could I have gotten better? So what I did was I read through all those questions, and then on the next test, which was, I just bought another practice test. I went through it, and then I was relieved because I got in the 90s, of course, like I was expecting to get in the 90s, right? And so sometimes these questions, the wording, like for example, number 63
Number 63, the wording is very, I know people have mentioned about the wording of some of these multiple choice, but the wording is not very clear on this, right? What do they mean by that? And so if that's the case, what you can do is you could put in, some explanatory, because I've already deviated from the book. I deviated from the book saying, which one's bigger? Minus 10 kilojoules or minus 30 kilojoules? Which one's bigger? Me, I'd say, I'd say minus, have you guys gone through this already? Yeah. Which one would I say? Me, for this class? 30. Petrucci would say 10. And so there's a difference already, but that's easy because you just keep clear. You know what they're talking about, right? You know what this person's talking about, Petrucci, versus what I'm talking about, Correct? And so this one, what I want to do is I want to make it clear, because how you answer this depends on your perspective on things. And so for me, this doesn't vary. I mean, no matter how you do the reaction, well, if you have QV, are there very many choices of doing the reaction? No, you have to do it under constant volume conditions. If you didn't do it under constant volume conditions, can we call it QV? Now, if you do it under constant volume conditions, is any work done? No, and so this has got to be true always, because we're restricted. We have a bomb, and that bomb restricts us. We can't do it under constant. How can we do a QV under constant pressure conditions? Would it even make any sense? No. And so why is he talking? I say this is true. Petrucci says this is false. Why do you think Petrucci says this is false? Let's try to understand his reasoning. Why does Petrucci say it's false? Do you think Petrucci says it's false because you could do it under constant pressure? No. Because this is like the speed limit. Did I look at the speed limit? The speed limit, let's say, is posted 25 miles an hour. That's the speed limit, regardless of how fast you drive. So I could be driving 60 miles an hour and 25. Does it matter? Does that change QV, the speed limit? No. And so it's fixed, right? And so what is he talking about? Because all of a sudden it's restricted, right? This should always be true, but why is he saying it's false? So this is me. This is Petrucci. So try to think, why is Petrucci saying that can change depending on how the reactions carry out?
It probably won't be if that's all the reaction carried out. If you carry out under constant pressure, then
Yeah, of course. If we carried this reaction out under constant pressure, then this might not be the heat of reaction, right? But why are we allowed to do that? Is my question. Because when you see that V, the V means you're restricted. Okay, if I do it under constant pressure, I might not get the same amount of heat, but does that change the speed limit? For example, the speed limit's posted 25. I decide I'm going to go 35. But does that change the speed limit? No. So to me, QV is like the speed limit. It's fixed, right? It's fixed. Of course I could do it under constant pressure, but is that going to change QV? Of course you could drive any speed you want, but is that going to change the speed limit? No, because the speed limit is, this is the speed you have to go according to, the maximum speed you have to go according to the law, right? And so, is that the reason why Petrucci is saying that the amount of heat this needs maybe some more clarification, this particular problem, because this particular problem,
I would agree that it's not so clear, you know, what I'm saying. And so how could this be made clearer? What would you like to know to make this question clearer?
Maybe be more specific to the question, probably.
Well, one thing they could do is they could just say the heat, you know, the heat evolved in the reaction equals QV. Then is that, you know, if they did that, right, then maybe, so the amount of heat we're going to get in this reaction is equal to QV. They could say something like that. But let's just go on here. Does QV, in other words, does QV change depending on how we do the reaction?
No.
No. Right? It's fixed. QV is equal to delta U. All right, so one of the things I could think of why they're thinking that this way is this. One of the things they're thinking is that, and this is the only thing I can come up with, is that Petrucci must be thinking of QV is equal to, well, there's two ways to do it. When we think of QV like this, we usually take it as, this is the heat as the reaction's written. You know? But as the reaction's written, sometimes you don't want to burn a whole mole. Sometimes you burn a half a mole, sometimes you burn 10 moles, right? And so the amount of heat is going to depend on the amount of stuff, the amount of reaction, times delta U. So is this why Petrucci is saying it's variable? Because, you know, we might burn different amounts? Does that make sense? It doesn't quite make sense for me. Because when we're thinking about delta U is going to be the QV, the heat per gram or the heat per mole, right? And it's the same thing. QV is always, you know, per gram, per mole. Depends on how much you burn, that's how much heat you have. But does the heat per gram change or the heat per mole change depending on how you do it? No, it's always the same. If you put 1 gram into the bomb, you're going to get 1 gram's worth of heat, right? Each time you put it into the bomb. And so this is why I say this is true for me. It doesn't change, you know. Of course, you're allowed to do the reaction any way you want, but QV says this is the amount of heat you're going to get in the bomb for this amount of reaction. Does that change? No. And so I say true. Okay, let's go to QP. Is QP always true? No. So I think we can agree on this. Why is QP not always true? Petrucci and I agree that it should be false. Why? Because it depends, how much heat you get at constant pressure depends on how much work, right? For example, you could get pretty much all heat, or you try to maximize the amount of work and minimize the amount of heat that you're generating by distance. So this is going to depend on how much work was done, and how much work is done is going to depend on how the reaction is carried out. So that's false. Delta U minus W.
False.
It's false. So I think we both can agree this is false because
It's under constant pressure. Like.
no, this doesn't have to be under constant pressure, but the amount of work depends on how other reactions carried out. So the amount of work changes. Delta U. This is true. Regardless of how I carry out this reaction, delta U is always going to be the same, right? This is true, the total internal. So I could have lots of work done, but that means a little bit of heat, because remember delta U is equal to Q plus W. And so the Q and the W will vary depending on how much work is done, but not delta U. And so delta U is true, regardless of how the reaction is carried out. How about delta H? Delta H says, Petrucci says false. Delta H changes depending on how the reaction is carried out. I say true, delta H doesn't change. Delta H doesn't change. Now how can we reconcile it? Well, we can reconcile that because I'm looking at kind of different perspective than what Petrucci is looking at. The perspective I'm looking at this, delta H, is this. Delta H is very restrictive. What are the restrictions on delta H? Delta H, we need to know the two things. We need to know the pressure and the temperature, right? And so if we're using a delta H, then we have to fix the pressure and we have to fix the temperature. And so if we go to delta H, let's say delta H at 1 bar and 298 Kelvin. Now does delta H change or vary depending on how you do it? And so this, again, I use the speed limit analogy because whenever we have a delta H, the delta H is fixed for a set of conditions here, pressure atmosphere conditions, right? That's going to fix the amount of work. Therefore, we always get the same amount of heat when we're under these conditions. Right, we wanted to make, the whole point of delta H is making heat a state function. What does that mean? Well, what that means is that if I burn 1 mole of methane and get this much heat, then somebody else who burns 1 mole of methane should get the exact same amount of heat as long as they started at 298 and ended at 298 and the pressure was constant at 1 bar. The starting pressure is 1 bar, the ending pressure is 1 bar or 1 atmosphere, right? Is that true or false? Will they get the same amount of heat? If I burn a mole of methane at 1 bar and 298 Kelvin here, will somebody else, let's say in San Diego, get the same amount of heat burning 1 mole of methane at 1 bar and 298 Kelvin? Yes. So regardless, they're going to get the same amount of heat, right? Now, what if the person in San Diego says, you know what, I'm not going to do it at 1 bar. I'm going to do it at 1 atmosphere. Will they get the exact same amount of heat? No, but did that change delta H?
No.
Did that change delta H? No, it didn't change delta H because this delta H is for 1 bar. They got to use a different delta H, which is for 1 atmosphere, but it did not change delta H. It doesn't matter if they follow my protocol or if they don't, right? But it's fixed. This is the beauty of the state function. It's always the same, right? It doesn't vary. And so why is Petrucci saying it varies depending on how you carry it out? Of course, delta H is going to vary depending on how you carry it out, right? But this delta H is not going to change, is it? You know, if you carry it out under different conditions, we got to use a different delta H.
But does delta H equal to delta U minus W?
Right. Right. Delta H is not only equal, it's defined as delta U minus W as long as W is restricted to not 0, P delta V work only. Remember, it has to be P delta V work, the natural work of system expanding and system contracting. And therefore, to me, this is a trick question, right? The trick question is, if I'm driving 35 in a 25 zone, did the speed limit change?
While I'm driving 35, I'm not driving the same speed, right? But the speed limit doesn't change. This is like, to me, when I see a delta H, this is like the speed, this is fixed, fixed anchor point. I might not be under those conditions, but I know this is always the same because it's fixed. Like the speed limit's always the same, it's fixed, right? And so this is where I disagree with Petrucci. I don't think this varies. I think this is fixed for the conditions. And so why is Petrucci saying it varies? If Petrucci's saying it varies because you can change the temperature, then of course. Or if you change the pressure, then of course it's going to change that, right? But that's like saying if I drive down a different road, now I'm on a 65 mile per hour road, oh, the speed limit changed, right? But was the speed limit still the same on the 25 mile an hour road? Did it change there? No. So do you see why I'm saying that it's fixed? Sure, I could go 65, but, I'm not on this road anymore. I'm on a different road, and on that road, it's fixed at 65. And so to help me understand why Petrucci is saying that this is variable, well, he's probably saying that this is variable because temperature can impact it, right? If we have a higher starting temperature and a higher ending temperature, that could change the potential energy. But the same thing here. Do you think delta U at 298 Kelvin is going to be the same as delta U at 2000 Kelvin? No, so he must not be thinking that temperature is variable, because temperature will change these numbers. And so what must he be thinking that's variable? It's got to be pressure. But if he's thinking, because here it doesn't matter what the outside pressure is, the outside pressure is going to have no impact on the inside pressure of the bomb, right? Here the outside pressure is going to change things, right? Like if you do this under 1 bar versus 10 bars, it's going to change things. But we're driving down a different road then. And so what I think he's calling this false is because of pressure, but you have to realize if the delta H's are always variable, then we have no fixed anchor points. There's nothing fixed. If the speed limit varies on the road, each time you drive down this exact same road, the speed limit one day is 25, the next day you're driving down the road, it's 35, the next day you drive down, it's 15. Would that drive you crazy? Yeah, and it doesn't work that way. That road is going to have 25. Delta H is the same thing. This pathway is going to have 25. That pathway is going to have 65, and it's fixed. There could be lots of different roads you could take. Yeah, there could be lots of different delta H's you take, but each individual delta H is for that set of conditions. And so here's where I disagree with Petrucci. I do not call this one false. I don't think it varies. Right? And if it did vary, then this table in the back of the book would be useless. When you go to Appendix D, there are 5 pages of delta H values. Each of these delta H values is at 298 Kelvin and 1 bar. If they're changing, then what's the use of writing them in a table? These are not variable. These are fixed. That's why we have them in the table. That's why we can look them up. Okay. So, Petrucci has this question, which one of these is true regardless? And he picked delta D, delta U. And it's just because he's just looking at it from a slightly different point of view than the way I'm looking at it. All right, so delta H is going to be a useful number because we can figure out the heats involved in chemical reactions. How much energy is going to be input or output in a particular reaction. And so delta H's are really useful, but how do we get delta H's? You know, if you're going to get a delta H, and what's more useful for us, a delta U or a delta H? Well, delta U seems to be more useful because it seems, and Patricia would agree to this, it seems fixed, right? Delta U is always the same. But for us, you know what's going to be more useful? Delta H. Why? I'm sorry?
The reaction release or the gain heat, we can calculate it by the
Okay, that's not exactly the reason why I was thinking is because do we do most of our reactions under constant pressure conditions or under constant volume? We do most of our reactions under constant pressure conditions, and delta H is going to be the amount of heat involved under constant pressure conditions. And so that's why it's going to be more useful. So delta H's, we're going to use those because 99% of the reactions we deal with are under constant pressure. And so let's take a look at using one of these. But the problem is how do we get delta H? And so let's look at number 107 as an example here. So we're looking at metabolism of glucose. When you metabolize glucose, you eat glucose, right? And then what happens to the glucose eventually? What is the glucose converted into? It's converted into energy, but atoms are neither created nor destroyed, so what becomes of the glucose itself? Right. What happens is when we metabolize glucose, we inhale oxygen, and then we exhale CO2, we produce some water, and energy, delta H. Now, the water here, is it going to be liquid water or gaseous water? This is going to be liquid water. And when we metabolize it, is our starting temperature and our ending temperature 298 Kelvin? No. Unfortunately, it's a little higher, so this might lead to a little bit of an error because what do you think our delta H value is going to be at? What temperature? Body temperature or? It's actually, if we had a biochem book, it would be at body temperature. A lot of them are body temperature, but this is not a biochem book, this is a general chem book, and it's going to be at room temperature, 298 Kelvin. But that's okay. And so here, let's balance this. We'll need 6 moles of O2. We're going to produce 6 moles of CO2 gas. And the first thing we're going to ask is delta H and delta U the same thing? Here. Okay, would it be close? What I'm asking is it going to be close to the same? Delta U and delta H?
Yeah.
Yeah. Delta U and delta H are about the same. And so there's different ways I can figure out how much heat is involved in this reaction. One, I can burn it in a bomb. Right? Take a mole of glucose, put it in a bomb, burn it. Or less than a mole. You don't have to take a mole. But we burn it and figure out how many kilojoules of heat or energy are released. But if I burn it, versus metabolizing it, won't it come out different? I mean, this looks like a combustion reaction, but in this, it says I'm metabolizing it, and so this is going to happen in a whole bunch of steps. It just doesn't, there's no flame inside your stomach. This is going to burn it, release the heat. Right? And so when I look at this is metabolism, not combustion. And so how can I figure out my delta H for metabolism versus the delta H versus burning it? And so what it boils down to is this is a state function. What do state functions depend on? The final and the initial. Does it depend on anything in between? No. And so as long as we start off at 298 and end at 298 or whatever temperature we are at, and as long as we start off at 1 atmosphere and end at 1 atmosphere, then we know the final and the initial.
You have to put 6 next to each.
Oh, yeah, okay, we gotta balance that. And so whether I burn it in a bomb or metabolize it, I should get about the same amount of energy. In fact, I should get exactly the same or approximately the same?
Approximately.
Why approximately the same?
It's one of the 6 figs. They're gonna be.
Okay, let's say I carried out all the 6 figs.
The volume changes.
Will I get the same amount of energy whether I burn it or metabolize it?
Because some energy is lost doing the wrong way.
I don't care about the energy lost. Energy lost, okay, the way you're thinking is about usable energy, right? I don't care about usable energy. I'm looking at the energy. You know, will I get the same amount burning it or metabolizing it, regardless of how much I actually use or lose? Will it be the same? It should be exactly the same, right? It doesn't matter. Yes, I'm going to maybe lose a lot more energy metabolizing it because maybe some of these steps aren't as efficient, but that loss, if I factor in the losses, then the total energy is going to be the same. And so here, one thing is I could burn this in a bomb. If I burn it in a bomb, what do I get? Delta U or delta H? Delta U. Once I get my delta U, then I have to convert it into delta H. Converting it into delta H here, we can look and assume that delta U and delta H are about the same. Why? Yeah, 6 moles of gas going to 6 moles of gas. And then we have some solid and liquid, but that's not going to change things much, right? And so I could get my delta H that way. The other thing I could do is I could burn it in the coffee cup. You know, styrofoam coffee cup isn't so good for burning sugar, is it? And then capturing that heat. And so likely I'd have to burn it in a bomb, get delta U, convert that into delta H. Fortunately, they're about the same, so I can make the assumption that delta H and delta U are about the same. And I want this. And so in other words, in order to get my delta H, I have to do calorimetry and some calculations. But calorimetry is a lot of work. And so is there an alternate way of determining delta H without having to do any calorimetry? And there is. 1, calorimetry. 2, we could try Hess's law. Hess's law says that, let's say reaction 1 we did calorimetry. Reaction 1 we know what the delta H is, delta H1. And then reaction 2, we have a delta H2. And then if we sum these, you know, and we get reaction 3, add these two up. Reaction 3 is going to have delta H3, which is going to equal delta H1 plus delta H2. And so if we know some prior data, maybe we could add up a couple of reactions to get our desired delta H. This is Hess's law. Okay, this is Hess's law by summing reactions like this. And then there's Hess's law by using formation reactions. Hess's law using formation reactions goes like this. Delta H of the reaction is equal to the sum of mu P delta H sub F P minus the sum of mu R delta H of formation of R. All right, to keep the conditions, you know, because delta H is going to depend on what? Temperature. And so what do you think most of our data is going to be at? What temperature? Room temperature. And pressure? Yeah, constant, and what do you think the pressure is going to be? 1 atmosphere or 1 bar? All right, so this is it. It doesn't have to be, but you know what this superscript 0 here means? This means standard thermodynamic conditions. Standard thermodynamic conditions is 1 bar for 1 atmosphere for the pressure and 1 molar for the solutions. There's no standard thermodynamic temperature, but most of the data you're going to see is going to be at a temperature of 298. So we'll just say under standard conditions at some temperature T. This F means formation of 1 mole of substance from the elements in their standard state under the given conditions. And so we could do an example here of a formation reaction. What is delta H of formation under standard conditions of glucose? Solid. Well, delta H of formation of glucose solid is this. We want to form how many moles of glucose? How many moles of glucose do we form for formation?
2? 3? 1 mole.
So we form 1 mole of substance from the elements. So what's the element carbon? C. And it's graphite. Graphite is the most stable form of solid carbon. So we say C, graphite carbon. We need 6 of those. How about hydrogen? Plus. What's the stable form of hydrogen at 298 in 1 bar? H2. Gas. And we need 6 of those. And what's the stable form of oxygen? O2 gas. And we need how many of these? 3. This is called a formation reaction here. It's forming 1 mole of the product or substance from the. And so we do Hess's law like this. We add up a bunch of these formation reactions, but since all of them have the same kind of starting materials, then we don't have to write out all the reactions, and we have a much simpler equation. The much simpler equation is this. And so we want to do the reaction that we were just looking at, and we want to do that without having to do calorimetry. And so let's use this equation to figure out what delta H is. So I want delta H of the reaction for 1 mole of glucose combusting. And that's going to equal the sum of the products. So the first product is going to be CO2. Nu R means, this is our nu P actually. 6 moles of CO2, this is the number of moles, times delta H of formation of CO2 gas. Okay, that's the first product. The second product, here's nu P. This is 6 moles of H2O liquid times delta H of formation of H2O liquid. We're going to have different heats depending on if it's a liquid, solid, or gas. So we got to make sure we put in. So this is the sum of the products minus the sum of the reactants. So we have 1 mole of glucose times the delta H formation of glucose plus 6 moles of O2 times the delta H formation of O2 gas. The delta H's of formation I find in Appendix D. Most of them.
Or the book. The delta H of formation of glucose is given in our book, minus 1273.3 kilojoules per mole.
Minus 1273.3 kilojoules per mole for glucose. This reaction, this delta H reaction is under standard conditions. And what's the temperature? Well, Appendix D, what's the temperature fixed at? Appendix D has a temperature fixed at 298 Kelvin. And so I know the temperature, 298 Kelvin. And so when I read this, I see Appendix D is 1 bar. 1 bar and 298 Kelvin. So we're good. Okay, so then I'll go look up CO2 in Appendix D.
Looking up CO2, I see that it is minus 393.5
Kilojoules per mole. Minus 393.5 kilojoules per mole. And then I look at H2O liquid.
H2O liquid is minus 285.8.
Minus 285.8 kilojoules per mole. And then I look up O2. You know what O2 is?
0 kilojoules per mole.
Why is O2 0 kilojoules? In fact, sometimes I don't even give it because I expect people to know. Why is O2, why would you be expected to know that delta H formation of O2 is 0? Because what's the definition of a formation reaction? The definition of formation reaction is the formation of 1 mole. So we're going to form 1 mole of O2 from oxygen. What's the most stable state of oxygen under ambient conditions? O2. So we form 1 mole of O2 from 1 mole of O2 at 298 Kelvin in 1 atmosphere. There's no change. It's the same thing. And so it's forming O2 from O2. This is going to be 0. There's 0 energy involved there. And so what does this come out to? Yeah, that's right. Negative 2802, is that what other people got? 0.3?
It's fine.
0.5? Yeah, 0.5. Okay, so what did we do? We just avoided having to do a calorimetry experiment. We were able to use Appendix D data to get how much heat will be released when you burn 1 mole of methane under
Room temperature.
1 bar of pressure and room temperature. That's good. And so the way we use this this value, once we have it, then we know it's minus 2802.5 kilojoules of energy for 1 mole of glucose. This is looking at the balanced chemical equation, which I erased earlier. And so this is the heat, or it would be minus 2802.5 kilojoules per 6 moles of O2 consumed, or minus 2802.5 kilojoules per 6 moles of CO2 produced. So let's say I burn some glucose and I exhale 3 moles of CO2. How much energy did I just generate? Well, 3 moles of O2, I generated about 1,400 kilojoules of energy, right? Or if I burn 10 moles, of glucose, I'm going to produce 28,000 kilojoules of energy. And so we could use these as conversion factors for doing stoichiometry.
And so let's go back to the problem itself. The problem is asking this. The metabolism of glucose yields CO2 and water as products. Heat released in the process is converted to useful work with about 70% efficiency.
So what does that mean? Heat produced is converted to work with about 70% efficiency. Wait, isn't this just heat? This is delta H. Delta H of the reaction. It's all heat, isn't it?
Because the work has already been factored out. So how can I convert this heat into work? Is that possible? Well, a lot of people say, sure, it's possible to convert heat into work. For example, if you burn coal, burning coal produces heat. And that heat you could use to heat up water to make steam. And the steam can be used to drive a steam engine, right? And so we could use the heat and convert it into work. And so is that what your body does? Inside your body, you have a little steam chamber and you're burning the glucose. It's producing this heat. There's somebody scooping the glucose into the fire, right? And you got this little steam engine is that how it works? No. That's not how it works. So yeah, we're going to produce all this heat. Where does all that heat go? Well, that heat must go into the muscle, right? And the muscle must have some way of doing work, right? And so this is another point of confusion. The reason I'm bringing this up is for those of you who have physics. Actually, has anybody had the Carnot cycle or talked about the Carnot cycle? Physics? No?
I think we gotta talk about it a few weeks later, not now.
Okay, not now. All right. The reason some people say, 70%, 80% efficiency, how can you convert heat into work with 80% efficiency? That violates the Carnot cycle, right? I say, no, it doesn't violate the Carnot cycle. But I've gotten into, because I have this feedback where people can dispute problems, so there's one problem they were talking about, and so it was an ongoing discussion about this, what is the maximum amount of work that heat can be converted into based on physics, right? But what we are doing is not the Carnot cycle. We aren't taking heat and then, driving some kind of machine using the heat. Do you know what we're doing? And so I wish I had this. Maybe I should just skip this, but the student was telling me this. How can you convert it with 70% efficiency? That violates Carnot. And the reason is because we aren't converting heat into work. You know what we're converting? We're converting potential energy into work. There's a difference. And the difference is this. Let's say I slide down the slide. What's going to happen? I lose a lot of energy. Where does that energy go? Into heat, right? Friction. And so I generate heat here. And so I have all this heat that I just generated by sliding. The slide's going to be warm, right? After I slide down it. Okay, so what they're saying is that this heat cannot be converted into work with high efficiency, right? And so what this means is, okay, what we're going to do is we're going to put water on here, try to boil the water to generate a steam generator to drive a machine. And so you're going to try to capture this heat and heat up some water to do something, right? Do you think that's very efficient? No, that's not very efficient. How we can seem to violate the Carnot is because we aren't collecting this heat. We try not to collect any heat, actually. What we try to do is we try to change the potential energy into work. Right? And so here, if I grease this slide, in other words, if I make a frictionless slide and I have a frictionless pulley, then you know what? If this were totally frictionless, then I can convert the energy pretty much all into work, or practically all into work. A little bit, obviously, it's going to be hard to avoid, right? But you see, I can convert a lot of energy into work here with high efficiency. It's because I'm converting the potential energy into work, not the heat into work. Okay. Well, anyway, that's my side trip, so. You could ignore this. Unless it bothers you. This person, it was bothering the person that the efficiencies were way too high. But anyway, going back to this, we're going to assume that 70%, wait a minute. Delta H is heat, right? And so if delta H is heat, then don't I have to burn the glucose, convert it all into heat first, and then convert it into work? Don't I have to do that? Right? This is the heat. In fact, this is called the heat of reaction. Delta H is known, aka heat of reaction. Therefore, all that must be heat before being work. True or false? That's false, because we know that delta H is also equal to delta U. And we restrict the work, right? If we restrict the work, sorry, I need to turn this on. We restrict the work but for delta H, but that doesn't mean we can't add more work, right? Delta H, we're only supposed to have work 1, let's say. But if we start adding more work 2, work 3, right? What's that going to do? That means our delta H is going to be converted into more work, less heat. Does that make sense? And so it's like this, but we can add on. And so yes, we're doing this under constant pressure conditions, but we're adding more work terms there. And therefore, the amount of heat we're actually going to generate is less, and the amount of work we're going to do is more.
And so what this problem is saying is, okay, we're going to leave this, we know the delta H is fixed. Delta H is 2802.5 kilojoules, right? And that should be all, it should be all heat. But what we're going to do is we're going to add some more work terms and then generate more work. And so what we're saying here is that 2802.5 kilojoules of energy is released. What we do with that energy is we can leave it as heat, or we can try to convert it into work. All right, so the first thing is, this is kilojoules per mole. This is the total energy, right? And if it's only 70% efficiency, what does that mean? That means for every, in this reaction, that means for every 100 kilojoules of energy that reaction spits out, then 70 kilojoules we can use to convert it into work. The other 30 kilojoules will be radiated off as heat. And so technically all of it's heat, but we can use it though, right? We can use that energy. Your body does this. Because when you eat glucose, sugar, does it convert it 100% into heat and no work? No. We need it to produce some work. And so in reality, or 70, in reality, we're only getting 70% of that as usable energy, right, for work. And so what does that come out to? $1961.75, is that what you guys have? I'll just call it usable for work. And so for every 1 mole of glucose, we only get about 1961.75 kilojoules that we can use for work. Calculate the mass of glucose metabolized by a 58.0 kilogram person in climbing a mountain with an elevation gain of 1,450 feet. And so if we have a 58.0 kilogram person, and they want to climb a mountain, this mountain is 1,450 meters. Okay, from physics we know if we put a rope around this person and just hoisted them up with frictionless pulley, then there's the minimum amount of work required to climb this. The minimum required work or energy is just going to be equal to the gravitational potential energy difference between there. And so the energy is just, this you don't have to know. This is just physics. And so don't bother. The energy is mgh. And so m is 58.0 kilograms. G, yeah, this is the minimum. But do you think climbing a mountain is going to take this? Don't you think it's going to take more energy than that? This is the absolute theoretical minimum. And so what they say is we're going to estimate that it's going to be 4 times the minimum amount to give us some buffer. And so, well, 4 times mgh. So that would be 4 times the mass, 58.0 kilograms, times g, 9.8 meters per second squared, times h, 1,450 meters. Actually, I need to know g to 3 sig figs. What is it to 3 sig figs? 981. 981, is that it? That sounds about right. That's all right. We don't have to be so precise here. And so how much energy is required? 300, 296,
720.
720 joules.
Oh, joules.
This would be joules. Kilogram meter squared per second squared is joules. So this would be 3,296.7 kilojoules required to climb the mountain. And so I have 3,296.7 kilojoules required for the work of climbing the mountain. And then we do this. We have 1,961.75 kilojoules of energy available for every 1 mole of glucose. And then glucose is, what is it? 180.2 grams per mole. And so this will tell us how many grams. Comes out to, I think, 303 grams. So about 300 grams of glucose. So, yes, we want to get these heats, delta H, delta U, so we can figure out the energies involved, and then we want to be able to use the energies in these problems. Yeah. And so the easiest way to get the delta H values for an unknown reaction is by using delta H as a formation. The values are in Appendix D. They're typically given on a test. The next easiest would be just using Hess's law proper. So let's take a look at using Hess's law to determine an unknown delta H. And we're going to do number 75. And lastly, calorimetry. Calorimetry is most difficult because that actually requires you to go into the lab and do an experiment. But number 75 is, let's say we know some delta H values of reactions. So CH4 plus 2 O2s yield CO2 plus 2 H2Os. Turns out all these are gases. And they give us a delta H value here. So it's minus 802 kilojoules. Looking at this, what do I know? What does this little superscript tell me? It's going to be 1 atmosphere or 1 bar. What about the temperature? Is there such thing as a standard temperature? No.
Room temperature.
Do you think this one's at room temperature? This is not at room temperature. Why? Because H2O is a gas. It can't be at room temperature. It's got to be greater than or equal to 373 Kelvin. And I know it because of this. And they need to specify the temperature. Did they? They didn't. All we know is it's got to be at some fixed temperature, and the temperature is high. I don't know what it is. But that's okay, because the next reaction has to be under the same set of conditions, otherwise I can't add them together. And so if I have one reaction at a high temperature and the other reaction at a low temperature, then Hess's law is not going to work. All the reactions that we're going to combine have to be under the exact same conditions. So this is going to be CH4 plus CO2. This is going to yield 2 COs plus 2 H2s. Okay, all these are gases also. And this is delta H2, they call it. They give us a value. I'm not going to write down the value yet. All gases. What kind of reaction is the first? What type of reaction is that?
The metathesis, acid base, or redox? Redox. What's the oxidizer, what's the reducer? Oxygen's the oxidizer. CH4 is the reducer. Okay, what's the next reaction? What type of reaction is that? Is that metathesis, acid base, or redox? Redox. Okay, what's the oxidizer? CO2 is the oxidizer and methane is the reducer. Now this is a weird reaction. This reaction, would you ever predict this to go? You know? Not really, because you would think CO2 is a very weak or very strong oxidizer. Very weak oxidizer. So when I look at this reaction, it doesn't look so favorable, does it? No, it doesn't. But anyway, could methane ever be the oxidizer? Maybe I got it backwards. Could methane ever be the oxidizer? Methane would never be the oxidizer. Why? Well, there are some electron-rich species that can act as an oxidizer. There's something special about methane. What is it? The oxidation state. The oxidation state on carbon is -4, which means when you look at the periodic table, if carbon has 4 extra electrons, it's the same as neon. Where would a 5th electron go? In other words, if it has 4 electrons, it's filled its valence shell. The 5th electron would have to go into the next higher energy shell, which is unstable. And so that doesn't happen. And so CH4 is only going to be a reducer. How about CO2? What's the oxidation state on CO2? Plus 4. Could CO2 ever be a reducer? In other words, could CO2 go to +5, +6?
No.
Why not?
It just stays that way.
One, you probably recall that I was talking about CO3. Remember carbon trioxide, carbon tetroxide, carbon pentoxide? You guys remember that? I said those are impossible or unlikely. Carbon trioxide maybe, but carbon tetroxide is impossible. Why? No more electrons. And in fact, if I did carbon trioxide, I'd have to take all the valence electrons and 2 of the core electrons. Core electrons are going to be very difficult, 10 times harder to remove than the valence electrons or more. And so basically when I hit +4, I've lost all its valence electrons and it stops. The only thing that we could do is attack the core, but unlikely. And so CO2 will never be a reducer. How about carbon monoxide? What's the oxidation state on carbon? +2. When carbon's +2, that means it could go either way. It could be an oxidizer or it could be a reducer. And so I want to show that. Well, anyway, this first reaction we know is very favorable. It's exothermic. Energy is going down. The second reaction here, let's take a look at it. Plus 247 kilojoules. Plus 247 kilojoules means this reaction is endothermic. You have to input energy to get this to go. But you know, the nice thing about Hess's law is this. What if we reverse this? Rather than going up, we start off here as reactants and down. If we reverse this reaction, 2 carbon monoxides and a hydrogen, then it will be -247. It'd be exothermic. And so it doesn't matter. This is the great thing about Hess's law because we could look at it in either way. But it looks like the reverse reaction is more favorable, isn't it? In this case, what is carbon monoxide acting as? The oxidizer or the reducer? Can hydrogen be both an oxidizer and reducer?
No.
Hydrogen's tricky. Yes, it can act as both. It can act as a reducer and go to H+. It's a great reducer. It could potentially act as an oxidizer and form H minus. H minus has a name, hydride. Typical hydrides are like the alkali metal hydrides. Alkali metals, because alkali metals give up electrons easily, so maybe hydrogen can oxidize an alkali metal, take the electron and form a hydride. And so both of these can go either way. This can go either way, this can go either way. So which way does it go? Which way it goes, you look at the products. And so over here, was carbon monoxide the oxidizer or the reducer? Was hydrogen the oxidizer or reducer?
Carbon monoxide, the reducer.
I'm out of time. This one's tricky. Let me write the next reaction. CH4 gas plus H2O gas
Goes to CO gas plus 3H2.
delta H3 under standard conditions is equal to
Plus 206 kilojoules.
I'm out of time. I want to
just write down the rest of this problem before time runs out. The reaction with the unknown,
delta H is this, CH4 gas plus
1/2 O2 gas
yields
CO gas plus
2H2 gas. Remember when we were doing
prediction of redox? With the prediction of redox, you use the chart there, the chart method, right?
how are these redox reactions? Are these redox reactions easy to predict? You know, oh, I'm going to oxidize methane using water. Does that sound like a good reaction? That sounds like a crazy reaction, because if I take methane and bubble it in water, I just expect the methane to bubble out of water. I don't expect to form carbon monoxide and hydrogen gas. Just because I write the reaction like this doesn't mean it's favorable. In fact, when you look at this delta H, it looks like the reverse reaction is favorable, because the reverse reaction is going down in energy. And so, yeah, carbon monoxide and hydrogen might form some methane and water. Right? But still, predicting carbon monoxide and hydrogen, what would you form? Well, you try to form stable stuff. But is that something easy to predict? No. And so this is why we have skeleton redox reactions. Skeleton, you just mix it and see what happens. You know, see what you form. And the skeleton redox, you know, you change the conditions a little bit, that could change your product. And so this is why there's a lot of just mix it and see what happens. But anyway, here what we want to do is we want to calculate the delta H for this. And I don't want to have to do this reaction, because normally when I take methane and burn it, I get CO2 and, not hydrogen, I get CO2 and water. But in this case, let's say I figured out some conditions to do this. Well, what would the delta H for this one be? Well, here I'm going to use Hess's law. And in Hess's law, we're going to try to add up these equations so that they equal this equation, and then see what to do about the delta H's. So we'll do that at the beginning of next time.
All right, any questions? No?